So the plan for today is to talk about energy-based model. So it's going to be another family of generative models that is closely related to diffusion models, which is what we're going to talk about next. So as a recap, remember this is sort of like the high-level picture which I think summarizes pretty well the design space when you're trying to build a generative model. You have data coming from some unknown data distribution, and you have IID samples from it. You always need to define some kind of model family, and then you need to define a loss function that basically tells you how good your model is compared to the data distribution. And we've seen that likelihood or KL divergence is a very reasonable approach, and that's pretty natural to use with autoregressive models, normalizing flow models, and to some extent variational autoencoders, because they give you ways to either exactly or approximately evaluate the probability of a data point, and so you can kind of like score how close p theta is to the data distribution by basically computing the KL divergence up to a constant, which is just like the likelihood assigned by the model to the data, which is kind of like a compression-based type of objective. And as we know, like maximum likelihood training is very good. It's a very principled way of training models, but you always have some kind of restrictions in terms of like, okay, how do you define this set of probability distributions? And you cannot pick an arbitrary sort of like neural network that will take as input the different axes, like the data point, and maps it to a scalar. Like it has to be a valid probability density or a valid probability mass function. And so in order to do that, you have to either use chain rule and break it down into a product of conditionals, or you have to use some kind of like invertible neural network to define the marginal distribution, or you have to deal with approximations and kind of like use a variational autoencoder. And then the other approach at the other extreme is to sort of like try to have as much flexibility as possible in terms of like defining the model family. And specifically, we're just gonna define the probability distribution implicitly by instead defining the sampling procedure. And the price that you have to pay is that you can no longer basically measure this kind of similarity up here using KL divergence. You have to essentially come up with a training objective that does not require you to evaluate probability of data points. Essentially, the only thing you have access to at this point is samples from the data and samples from the model. And so you have to come up with some kind of two-sample test, some kind of likelihood-free way of comparing how similar the real samples from the fake samples are. And GANs are one way to do that, where you have this minimax objective, where you're trying to train a generator to produce samples that are hard to distinguish from the real ones, as measured by some discriminator that is trained in the innermost maximization problem to do as well as it can to distinguish real versus fake samples. And we've seen that that's, under some conditions, this is principled in the sense that if you had access to extremely powerful discriminator, then you could, to some extent, approximate the optimization of an F divergence or even a Wasserstein distance. But in practice, although it's true that you can use essentially any architecture you want to define the sampling procedure, training this kind of minimax with these minimax objectives is very tricky because we don't have likelihoods. You have to do minimax optimization, which is unstable. It's hard to track progress. It's hard to know whether you've converged or not. It's hard to evaluate whether one model is better than the other because you cannot just look at the loss. And you have mode collapses, and so all sort of issues that arise in practice when you try to train an adversarial type model. And so what we're going to see today is another way of defining kind of like a model family. So kind of like a different way of parameterizing probabilistic models that is called an energy-based model. And what we'll see is that this will allow us to essentially lift all those restrictions that we had on the kind of neural networks you can use to define a valid probability density function or a valid probability mass function. So that's the main benefit of using this kind of energy-based models, extreme flexibility. And to some extent, they will allow us to have some fairly stable training procedure, in the sense that it's still going to be based on maximum likelihood or other variants of losses that are sort of like fully, that are kind of like taking advantage of the fact that you have a probabilistic model and not just a sampling procedure. These models tend to work pretty well. They give you fairly high sample quality, and we'll see they are very closely related to diffusion models, which are actually sort of like state-of-the-art models right now for a lot of continuous modalities like images, videos, audio, and others. And as another benefit, you can also compose energy-based models in interesting ways. And so we'll see that that's another thing you can do, that you can take different kind of generative models and you can combine them. Because that essentially it's one way of defining an energy-based model, and that allows you to do interesting things like essentially combining different concepts and combining different kinds of model families together, like a flow model and an autoregressive model. And we'll see that that's also beneficial in some settings. So the kind of high-level motivation is the usual one. We want to define a probabilistic model. So we want to define a probability distribution because that's kind of like the key building block. We need to define this green set here that we're optimizing over. And if we can do that, then we can just couple that with a loss function and you get a new kind of generative model. And to some extent, this is just a function. It's a function that takes x as an input, where x could be an image or a sentence or whatever, and maps it to a scalar. Right? So it seems pretty straightforward, but the key thing is that you cannot pick an arbitrary function. These valid probability density functions or probability mass functions in the discrete case, they are special kind of functions in the sense that they need to satisfy certain constraints. The first one is that they have to be non-negative. So given any input x, the output scalar that you get from this function has to be a non-negative number. And this, we'll see, is not a particularly hard constraint to enforce. The more difficult one is that they have to be normalized. So because we're working with probabilities, it has to be the case that if you look at all the possible things that can happen and you sum up their probabilities, you get 1. Or if you're working with continuous random variables, if you integrate the probability density function over the whole space, you should get 1. And so, again, this is basically due to the fact that essentially the probabilities, if you go through of all the possible things that can happen, have to sum to 1. And that's a much trickier kind of constraint to enforce. That's really the hard constraint to enforce, and that's because essentially the reason we have to enforce those strange architectures like autoregressive models or flow models is basically because we have to enforce this normalization constraint. And enforcing that is tricky, and if you take an arbitrary neural network, it's not going to enforce, it's not going to satisfy that constraint, and enforcing that is not straightforward. And so again, sort of like if you think about the first constraint, it's not a very hard property to satisfy. So it's not hard to come up with a very broad set of or families of functions that are guaranteed to be non-negative given any input. And in fact, if you take an arbitrary function, let's say an arbitrary neural network, it's pretty trivial to change it a little bit and make sure that the output is guaranteed to be non-negative. Right? And so one thing you can do is you can take an arbitrary neural network f theta. If you just square the output that it produces, you get a new neural network g theta, which is also very flexible because it's basically very similar to the f theta that you started with, and it's guaranteed to be non-negative given any input. Or you can take the exponential. again, given an arbitrary neural network f theta, if you just basically add an extra layer at the end, which takes the output and passes it through this exponential nonlinearity, then you get a new neural network which is guaranteed to be non-negative. Or you could take the absolute value, or I'm sure you can cook up many, many other ways of transforming a neural network into one that is just as basically flexible, where you just add a new layer at the end that is guaranteed to make the output non-negative. So that's not hard to do. The tricky part is to guarantee that basically if you go through all the possible inputs that you can feed through this, let's say, neural network, and you sum up the outputs, you get one. Or if you have a continuous setting where the inputs are continuous, then the integral over all possible inputs to this neural network has to be 1. And I guess one way to think about it is that, and why this is important if you're building a probabilistic model, is that this is basically enforcing that kind of like the total probability mass is fixed. So if you're thinking about the role of a probabilistic model as being, or the meaning of outputting, of computing P of X, is you're saying what is the probability that the model assigns to one particular X, which could be an image or could be some sentence in a language modeling application. The fact that basically the sum of all the probabilities is 1 is kind of enforcing this fact that essentially the total volume is fixed. And so if you increase the probability of one data point, you're guaranteed that the probability of something else will have to go down. So the analogy is that there is a cake and you can divide it up in many different ways. But if you make one slice bigger, then the other ones will have to be to get smaller, inevitably. And we need this kind of guarantee so that when we increase the probability of the data that we have in the training set, by increasing kind of like the slice of the cake that we assign to the samples we like, the ones that are in the training set, we're automatically reducing the probability of other things, which are, in the case of a generative model, the things that basically we don't like. And again, enforcing the non-negativity constraint, which is basically saying, with this analogy, that the size of each slice is non-negative, is easy, but enforcing this constraint that sort of like the volume is fixed. Here in the definition, it's 1, but as long as you can keep it fixed, basically that's fine, because you can always divide by the constant. But enforcing that basically, regardless of how you choose your parameters theta in your neural network, you're guaranteed. That's sort of like if you go through all the possible inputs, or if you sum over all possible inputs, or you take an integral over all possible inputs, and you look at the output value, you get a constant, which does not depend on theta, does not depend on the parameters of the neural network. That's hard. Like, you can always compute what is the total kind of like a normalized probability that is assigned by a neural network if you go through all the possible inputs. There is always going to be some number. Like, if you go through all possible inputs and you evaluate the output of the neural network, you sum them up, you're going to get a value. But in general, that value is going to depend on theta, it's going to depend on the parameters of your neural network, and it's not going to be 1, it's not going to be something fixed. Unless you choose g theta, you choose your function family in some very special way, like an autoregressive model, or with invertible architectures that's sort of like guaranteed by design that no matter how you choose your parameters, the total mass or the total volume is basically fixed. And the analogy here is, in the discrete case, you sum over all possible inputs. In the continuous case, it's the integral that you have to worry about. And so that's basically the hard constraint to enforce. Like, somehow what we need to be able to do is we need to be able to come up with a family of functions that are parameterized by theta. Ideally, these functions should be as flexible as possible, meaning that you would like to choose essentially an arbitrary neural network or very deep neural networks or very no kind of constraints on the kind of layers that you can choose. It's easy to enforce that the function is non-negative, but it's very hard to enforce that the volume is fixed to some value. Yeah.
I mean, we still need one function that satisfies it if you're going to redistribute the pi, though. Like we need a starting point.
So yeah, basically that's sort of like the idea of energy-based models, is that you can basically, as long as you can compute the total area of the pi or the total amount of pi that you have, then you can define an you can define a valid probabilistic model by basically just dividing by that number. And that's basically the idea behind energy-based models. Like the fact is that kind of like even given a non-negative function g theta, you can always define a valid probabilistic model by basically dividing by the total volume, by the total area, the total size of the pi, by dividing by the integral over all possible inputs of the unnormalized probability. And that defines a valid probability distribution because this object is now normalized. So if for every theta, you can compute these unnormalized probabilities, the size of each slice of the cake, and at the same time you can also compute how big is the cake, then and you divide these two, then you get something that is normalized because it's kind of like a ratio. And that is basically the main idea behind energy-based models, is to just bite the bullet and be willing to work with probability density functions or probability mass functions that are defined by normalizing objects that are not necessarily normalized by design, by dividing by this quantity z theta, which is often called the partition function, this normalization constant, the total volume, the total amount of unnormalized probability that we need to divide by to get a valid probabilistic model. And you can see that if you are willing to divide by this z theta, you can get a valid, you get an object that is normalized, because if you integrate the left-hand side here, you get, and you swap in the definition, which is g theta over the normalization constant, you basically get the integral over all the possible things that can happen in the numerator, the integral of all the possible things that can happen in the denominator, and when you divide them, you get 1 by definition, basically. And so basically, as long as you have a non-negative function, g theta, you can always define a valid normalized probabilistic model by dividing by this normalization constant, by this partition function, by the integral over the scalar that you can that is well defined, which is just the integral over all possible inputs, or the sum over all possible inputs in the discrete space of these unnormalized probabilities that you get by just using g theta. And as a few examples that you might have seen before is, or one way to go about this is to choose functions g theta for which this denominator, this normalizing constant, this partition function is basically known analytically. Like in general, we might not know, this integral might be tricky to compute, but if we restrict ourselves to relatively simple functions, g theta, we might be able to compute that integral in closed form analytically. Just for example, if we choose g to have a very kind of simple form, which is just like the kind of relationship that you have in a Gaussian PDF. So g is just basically a squared exponential, and g now has two parameters, mu and sigma, and this non-negative function is just or e to the minus x minus mu squared, basically is divided by the variance sigma squared. This function is non-negative. By itself, it's not necessarily normalized, but it's a simple enough function that you can actually compute the integral analytically. Like we have a closed form solution to that. And the total volume is just the square root of 2 pi sigma squared. And indeed, if you take this expression of G and you divide it by the total volume, you get the Gaussian PDF. So you can think of that strange kind of scaling factor that you have in front of the Gaussian PDF as being basically the total volume that you have to divide for if you want to get a normalized object. Or you could choose, okay, let's choose G to be just an exponential that looks like this. You have a single parameter, lambda, and g of x is e to the minus lambda x. Again, non-negative function by itself is not necessarily normalized, but you can compute the volume in closed form. It turns out to be just 1 over lambda. And so you can actually get, if you divide these two things, you get a valid PDF, which is the one corresponding to the exponential distribution. And more generally, there is a broad family of distributions that have PDFs that basically have this form. It's kind of similar to what we have up here. It's also an exponential of some dot product between a vector of parameters theta and a vector of functions of sufficient statistics t of x. Not super important, but it turns out that there is a volume here, which is just the integral of the unnormalized probability. And then if you divide by that quantity, you get this family of distributions that are called the exponential family, which captures a lot of known commonly used distributions like normal, Poisson, exponential, Bernoulli, and many more. And so this kind of setting where you start with a negative function and you somehow restrict yourself to functional forms that are simple enough that you can compute the integrals analytically, they are pretty powerful in the sense that these are very useful kind of building blocks, useful in many applications. But you can see that sort of like you can't choose an arbitrary G. If you choose some really complicated thing or you plug in a neural network, you might not be able to compute that integral analytically. There might not be a closed form for that partition function theta or the total and normalized probability, and that's sort of like where energy-based models come in. Like, how do we kind of go from this kind of setting where everything is simple, kind of handcrafted, can be solved analytically in closed form, to something more flexible where we can start to plug in much more complicated kind of functions here, like neural networks, essentially. And now, these simple building blocks, like Gaussians, exponentials, and so forth, they're still pretty useful in the sense that what we've been doing so far, like using autoregressive models or even variational autoencoders, latent variable models, are essentially kind of like tricks for composing simple functions that are normalized by design and building more complicated probabilistic models that are, again, by construction, sort of like guaranteed to be normalized. And so, as we can see that in some sense an autoregressive model is basically just a way of defining joint probability distribution or joint probability density function that is normalized by design because it's a product of conditionals that are normalized, that sort of like are Gaussians or are exponentials, or like they are the ones for which we know how to compute these integrals, these partition functions analytically. And so if you imagine you have two of these objects that are guaranteed to be normalized, like family parameterized by theta, and another family here that is parameterized by theta prime, where theta prime can be a function of x, as long as for every theta prime, the distribution that you get over y is normalized. This full object that you get by multiplying them together is guaranteed to be normalized. So if you look over, if you try to, if you multiply together two objects that are basically by construction normalized, like the marginal over x and the conditional over y, where the parameters depend on x, you get something that is normalized. It's basically what we do in an autoregressive model, right? You define the joint as a product of conditionals, and if you look at the integral over all possible inputs of the joint, you get something that is by design basically normalized. And the reason is that if kind of like by construction, the distribution over y is such that it's normalized for any choice of the parameters, and the choice of the parameters can depend on the value that x can take, then by design, sort of like the integral over y is guaranteed to evaluate to 1, regardless of the choice that you have for x. And then when you integrate over x, again, that object is normalized, and so you get, once again, something that where the full joint distribution is guaranteed to be normalized and to integrate to 1. And so the object in here, it's essentially one way of thinking of the conditional of y. The probability over y is, let's say, a Gaussian, where the parameters depend on the value of x, right? This would be one setting where this would show up if you have an autoregressive model, where, let's say, p of x is a Gaussian, p theta of x is a Gaussian, so here theta could be the mean of the standard deviation, and the distribution over the second variable or the second group of variables is again a Gaussian, where the parameters of the Gaussian, theta prime, are allowed to depend on x. For example, you compute the mean and the standard deviation as a function of the previous variable in the ordering, then you have an object that is guaranteed to be normalized by design. So you can think of kind of autoregressive models as a way of combining objects that are normalized, simpler objects, and putting together a more complicated one, a joint distribution that is, again, guaranteed to be normalized by design. Which is a product of normalized objects, and then if you slide kind of like these integrals in, you can kind of, all the integrals evaluate to 1. When you integrate out the conditionals, they all evaluate to 1, and the full object is guaranteed to be normalized. And to some extent, even the latent variable models can be thought as a way of, again, kind of like combining normalized objects and building a more complicated one that is, again, guaranteed to be normalized. So if you have two densities, p theta and p theta prime, that are normalized, and then you take a convex combination, it's like alpha p plus 1 minus alpha p prime for any choice of alpha or between 0 and 1, you get another density which is guaranteed to be normalized, right? Because if you integrate it out, again, you get something that basically the first integral evaluates to alpha because p theta is normalized. The second integral evaluates to 1 minus alpha because theta prime is normalized. So again, you get an object that is normalized. And that's basically what happens in a variational autoencoder, where you have this kind of mixture in behavior. The conditionals that you have in the encoder, in the decoder, are simple normalized objects like Gaussians, and you're taking a mixture of them, and by doing that you define a marginal, which is again sort of like normalized by construction. And so you can kind of think of what we've been doing, like building autoregressive models or latent variable models, as trying to kind of like clever ways of combining simple normalized objects and building more complicated objects that are normalized by design. But this is sort of like enforcing some restrictions still in terms of like how complicated the final object is, and you have to sort of like follow these rules to construct objects that are guaranteed to be normalized. So what energy-based models do is they try to break this this constraint and try to go beyond basically probability densities or probability mass functions that are guaranteed to be normalized, for which basically because the normalization constant is known analytically. And instead, we're going to be working with settings where this normalization constant, this partition function z theta, is something that we'll have to maybe deal with, that either we're not going to be able to compute it or we're going to approximate it, but it's not going to be it's not going to be something that is known to take up, like say value 1 for any choice of theta. It's going to change as a function of theta in some complicated way, and we're just going to have to basically deal with it. And so specifically, we're going to be looking at models of this form, where we have a probability density function over x, which is parameterized by theta, and is defined as the exponential of f theta, because we need to make sure that the function is non-negative. And then, so this is kind of like the unnormalized probability, the exponential of f theta, and then we divide by the partition function to get an object that is actually normalized. And so you can start with an arbitrary, basically neural network f theta, you take the exponential, you get a non-negative function, and then you define a valid probability density function by dividing by this partition function, by this normalization constant, which is just the integral, basically, of this unnormalized probability. And so that's all, basically, that's the definition of an energy-based model. It's very flexible because you can choose essentially an arbitrary function, f theta, and that defines a valid probability density function. We chose specifically the exponential here instead of, let's say, squaring f theta for several reasons. The first one is that it allows us to capture pretty nicely, pretty easily, kind of like big variations in the probability that the model assigns to different x's. So if you're thinking about modeling images or even text to some extent, you might expect very big variations in the probabilities that the model assigns to, let's say, well-formed images as opposed to pure noise. And so it makes it easier to model these kind of like big variations in the probability if you take an exponential here, right? Because small changes in f theta, which is what your neural network does, will lead to big changes in the actual probabilities that are assigned by the model. You could also do it with, just if you take a square here, but then that would require bigger changes, sort of like in the outputs of the neural network. So it's going to be much less smooth.
What is energy by definition?
Yeah. So that will come up in the next bullet. Yeah. So, yeah.
Is this not softmax?
Softmax is an example of that. Yeah, that's a good point. Yeah, like a softmax is one way of doing this and essentially mapping the output of a neural network, which is not necessarily a valid probability, a valid categorical distribution over, let's say, the outputs that you're trying to.
I'm a little bit confused is that because you mentioned latent variable earlier. But in, say, our VAE, we use softmax to compute the reconstruction likelihood. So how is that how is that not an energy-based model?
So energy-based models is a very general term in the sense that, you could even think of an autoregressive model as being a type of energy-based model where by construction, kind of like z theta is always guaranteed to be 1. So this is just like a very general type of model where we're going to be able to take an arbitrary neural network, let's say f theta, and get a valid probability density function from it.
It's not kind of a new concept. It's not mutually exclusive.
It's more general because it doesn't have to be like z theta doesn't have to be exactly 1, and it doesn't have to be like in the Gaussian case some known. Like z theta might not be something that is known analytically. Like you might not be able to know that this integral evaluates to the square root of 2 pi sigma squared, right? Because that only happens when f theta is very simple. Like if f theta is x minus mu squared, then you get a Gaussian, and then you know how to compute that integral analytically. But in general, you don't have to.
In the latent variable, the formula you showed in the previous slide, so is that kind of just shows like the probability of a mixture of Gaussian prior or something?
Yeah, it's basically like if you're thinking about the problem more abstractly as saying, okay, how do I come up with a way of designing functions that are non-negative and they're guaranteed to have some fixed integral? Like how would you go about it? Right? One way is to kind of like define a set of rules almost like an algebra where you can start from objects that have the properties you want, and you can combine them to construct more complicated objects that again have the properties you want. And one way to do it is what I was showing here, is like you can take linear kind of combinations of these objects, like convex combinations of these objects, and that's one way of defining a new object that still has the properties you want in terms of simpler objects.
But like, which part in this function represents the latent variables?
In the latent variable would basically be the alpha is like the alphas are the probabilities that the latent variable. Here, basically, this would correspond to a latent variable model where there is a single latent variable which can only take two different values. And it takes value, the first value with probability alpha, the second value with probability 1 minus alpha. And so that gives you that sort of behavior.
Thank you.
But I think what you were saying about the softmax is another good example of essentially an energy-based model. Like it's a softmax is a way of defining. It's essentially has, if you think about a softmax layer, it has exactly this kind of structure, and it is in fact a way of defining a probability distribution over a categorical, basically a random variable, which is the predicted label, in terms of a function f theta, which are just the raw outputs of your neural network, which might not be necessarily normalized. So the softmax is exactly this kind of thing, but the softmax is a case where this partition function, this normalization constant, can be computed analytically, because you only have, let's say, k different classes. So the softmax will involve, in the denominator of the softmax, you have a sum over k different possible outputs. And so in that case, this normalization constant can actually be computed exactly. We're going to be interested in settings where x, this integral, is going to be very difficult to compute exactly, because x is very high dimensional. So there is many different, if you think about a distribution of images, x can take an exponentially large number of different values. And so if you have to integrate over all possible images, that's going to be a very expensive kind of computation, practically impossible to compute. So that's kind of like the difference between the softmax style computation and what we're doing here. Cool. And so yeah, why do we use exponential? Because we want to capture big variation. The other reason is that, as we've seen, many common distributions like the Gaussian and exponential and all the ones in the exponential family, they have this kind of functional form. They have this flavor of something like exponential, of some simple function in the argument of the exponential. And the reason these distributions are so common is that they actually arise under fairly general assumptions. So if you know about maximum entropy modeling assumptions, which is basically this idea of trying to come up with a distribution that in some sense fits the data but minimizes all the other assumptions that you make about the model, then it turns out that the solution to that kind of modeling problem has the form of an exponential family. So that's why they are called energy-based models, because this also shows up a lot in physics. Think about the second law of thermodynamics. And in that case, minus f of x is called the energy. And there is a minus because if you think about physics, configurations where you can imagine x are the possible states that the system can be in, states that have lower energy, so high f theta, should be more likely. So that's why there is the minus sign, but that's why they're sort of like called energy-based models, because they are inspired by statistical physics, essentially. So, cool. So that's the basic kind of paradigm of an energy-based model. You start with an arbitrary, essentially arbitrary neural network, f theta. You take an exponential to make it non-negative, and then you divide by this normalization constant, this partition function, which is just the integral of this unnormalized probability. And this, for any choice of theta, it defines a valid probabilistic model. So it's guaranteed to be non-negative, it's guaranteed to sum to 1. And so from the point of view of the flexibility, this is basically as good as it gets. There is no restriction essentially on the f thetas that you can choose, which means that you can plug in whatever architecture you want to model the data. The cons, that there is many, as usual, there is usually some price to pay. If you want flexibility, you're basically making less assumptions about the structure of your model, and so there is a price to pay computationally. And one big negative aspect of energy-based models is that sampling is going to be very hard. So even if you can fit the model, if you want to generate samples from it, it's going to be very tricky to do that. So it's going to be very slow to generate new samples from an energy-based model. And the reason is that basically evaluating probabilities is also hard, because if you want to evaluate the probability of a data point, you basically, it's easy to get the unnormalized piece, this exponential of f theta. You just feed it through your neural network, you get a number that gives you the normalized probability. But somehow to actually evaluate a probability, you have to divide by this normalization constant, which is in general very expensive to compute. And which kind of like hints at why also sampling is hard. If you don't even know how to evaluate probabilities of data points efficiently, it's going to be pretty tricky to figure out how to generate, how to pick an X with sort of like the right probability. Even evaluating the probability of a data point is hard.
Why sampling is hard for this energy-based model, since we could learn a form of PCFX.
If we could learn?
If we could already learn a form of P state of X.
Yeah, so sampling is hard. Like even if somebody gives you the P theta, the function, it tells you, okay, here's the model. Basically, the problem is that sampling is hard because, first of all, there is no order. Like if you think about an autoregressive model, there is no ordering. So the only thing you can do is, as we'll see, there's going to be some kind of like local type procedure where you can try to do essentially Markov chain Monte Carlo kind of methods to try to go look for X's that are likely essentially under the model. But even evaluating likelihoods is not possible. It's hard because that requires the normalization constant. And so in general, there is not going to be an efficient way of generating samples from these kind of models.
So it means that the input X has no order with...
Yeah, so you can imagine, there is no ordering. Like X is just a vector, or it's your data, and you just feed it into a neural network, and then you get a number that is kind of like the normalized probability. But that doesn't tell you how likely that data point is until you know how likely everything else is. So you need to know the normalizing constant, the partition function, to know, even just to know how likely a data point is. And so as you can imagine, even figuring out if you were to sample from a distribution like that, it's pretty difficult, right? Because you cannot even, if you wanted to even just invert the CDF kind of thing, that would require you to be able to evaluate probabilities, and so it's just a very kind of tricky thing to do. Yeah.
So I guess the cons really nullify the flow, right?
Yeah, as we'll see. I mean, it's hard but possible, and in fact, if you think about a diffusion model, is essentially doing this. So it's not going to be as straightforward as just the sampling from a bunch of conditionals, like in an autoregressive models. We're going to have to do more work to kind of sample from the model. Evaluating probabilities will also require some approximations or some other kind of techniques that are much more sophisticated. But yeah, this kind of idea of being able to essentially use an energy-based model and be able to use whatever arbitrary architectures to model to model your data actually paid off in a big time if you think about the success of diffusion model, which I think largely depends on the fact that we're allowed to use very complicated neural networks to model the data. And there is also no feature learning in the sense that, at least in this vanilla kind of formulation, there is no latent variables, but I guess that you can add. So it's not really a big con in this case. And the kind of like fundamental issue, the reason why all these tasks are so hard is the curse of dimensionality, which basically in this case means that because we want to have a lot of flexibility in choosing f theta, we're not going to be able to compute this integral analytically. It's not like the Gaussian case. So we're not going to be able to compute that in closed form. And if you wanted to basically brute force it or use numerical methods to try to approximate that integral, the cost that you pay will basically scale exponentially in the number of variables that you're trying to model. And essentially, if you think about the discrete case, there is kind of like the number of possible x's that you would have to sum over grows combinatorially, and the number of grows exponentially in the number of dimensions that you have. And essentially the same thing happens also in the continuous world. Like if you were to discretize and have like little units of volume that you use to cover the whole space, the number of little units of volume that you need will grow exponentially in the number of dimensions that you deal with. And so that's essentially the key challenge of these energy-based models. Computing this denominator is going to be hard. So on the one hand, we're going to get flexibility. On the other hand, there is this big computational bottleneck that we have to deal with, the partition function, basically. And the good news is that there is a bunch of tasks that do not require knowing the partition function. For example, if all you have to do is to compare, you have two data points, x and x prime, and all you have to do is to know which one is more likely. So you just want to do a relative comparison between two data points. So you cannot necessarily, even though you might not be able to evaluate the probability of x and the probability of x prime under this model, because that would require knowing the partition function. If you think about what happens if you take the ratios of two probabilities, that does not depend on the normalization constant. Right? If you take the ratio, they both the numerator and the denominator, they are both normalized by the same constant, and so that basically goes away. If you think about the slices of pi, if you're trying to just look at the relative size, you can do that easily without knowing the actual size of the pi. And which means that we can check, given two data points, we can check which one is more likely very easily. Even though we cannot know how likely it is, we can check which one is more likely between the two. And this is going to be quite useful when we design sampling procedures. You can still use it to do things like anomaly detection, denoising, as we'll see when we talk about diffusion models, also kind of like relies on this. And in fact, people have been using kind of like energy-based models for a long time, even for a variety of different basic kind of like discriminative-like tasks. Like if you think about object recognition, if you have some kind of energy function that relates the label y to the image x, then and you're trying to figure out what is the most likely label, then as long as you can compare the labels between them, then you can basically solve object recognition. These kind of energy-based models have been used to do sequence labeling, to do image restorations. As long as the application kind of like requires relative comparisons, the partition function is not needed. And as an example, we can think about the problem of doing denoising, and this is kind of like a old school approach to denoising, where we have a probabilistic model that involves two groups of variables. We have the we have a true image y that is unknown, and then we have a corrupted image x, which we get to observe, and the goal is to infer the clean image given the corrupted image. And one way to do it is to have a joint probability distribution, which is going to be an energy-based model. And so we're saying that the probability of observing a clean image y and a corresponding noisy image x has this kind of like functional form where there is the normalization constant, and then it's the exponential of some relatively simple kind of function, which is the energy or the negative energy in this case. And this function is basically saying something like there is some relationship between the ith corrupted pixel and the ith clean pixel. For example, they should be fairly similar. So whenever you plug in xi and yi, configurations where xi is similar to yi should be more likely, because we expect the corrupted pixel to be more likely to be similar to the clean pixel than to be very different from it. And then maybe you have some kind of like prior over the images that is saying, what choices of y are more likely a priori, and maybe you have some kind of prior that is saying neighboring pixels tend to have a similar value. Then you sum up all these interaction terms, one per pixel, and then maybe you have a bunch of spatial local interactions between pixels that are close to each other in the image, and that defines an energy function. And if you want to do denoising, if you want to compute given an x, you want to figure out what is the corresponding y, what you would do is you would try to find a y that maximizes p of y given x. And even though the probability depends on the normalization constant, basically you can see that the normalization constant doesn't matter. So as long as you want to find the most likely kind of solution, what is the actual probability? So what is the 1 over z just becomes a scaling factor, and it doesn't actually affect the solution of the optimization problem.
Y's dimensionality is kind of large, like in real images.
So it might be still tricky to solve the optimization problem in that you're still optimizing on a very large space, but at least it does not depend, as long as you're maximizing the actual value, basically all the y's are going to be divided by the same z. So again, it doesn't matter as long as you're going to be able to compare two y's, and that's all you need if you're trying to. So x will show up in the energy, but again, x is fixed.
Yeah, we don't have to sum over all that.
Yeah, exactly. So it's really all about, there are a bunch of tasks. Basically what you care about is doing comparisons. And to the extent that the task only involves comparisons, then you don't actually need to know the partition function. You might still need to have the partition function if you want to train the models. That's kind of like what's going to come up next. But kind of like at least doing comparison is something you can do without knowing the partition function.
Yeah, like for comparison case, we sort of end up getting away with knowing z value. Like I also kind of observe that if we take the derivative of the energy functions, right, and then it also goes away.
Yeah.
Would that have some implications?
Yeah, so that's gonna come up towards one of the last slides. That's another nice thing is that the derivative also does not depend. The derivative of the log probability does not depend on the normalization constant. So we're gonna be able to use it to define basically sampling schemes. Yeah. Cool. Now another thing you can do is you can combine various models. So let's say that you have a bunch of probabilistic models. For example, it could be even different model families, maybe a pixel CNN, a flow model, whatnot. You could imagine that each one of them is kind of like an expert that will individually tell you how likely is a given x according to each one of these three models. And you could imagine what happens if you try to ensemble these experts. And for example, you could say, if all these experts are sort of like making judgments independently, it might make sense to ensemble them by taking a product. And the product of these objects that are normalized by themselves is not going to be normalized, but we can define a normalized object by sort of like dividing by this normalization constant. And kind of intuitively, this kind of way of ensembling behaves like an AND operator, where as long as one of the models assigns 0 probability, then the product evaluates to 0, and this ensemble model will assign a 0 probability. While if you think about the mixture model, where you would say alpha p theta 1 plus 1 minus alpha p theta 2, that behaves more like an OR, where you're sort of saying as long as one of the models assigns some probability, then the ensemble model will also assign some probability. Taking a product behaves more like an AND. But it's much trickier to deal with because you have to, take into account the partition function. And but this allows you to combine energy-based models, combine models in an interesting way. You can have a model that is kind of like produces young people, and then you have a model that produces females, and then you can combine them by multiplying them together, and then you get a model that is putting most of the probability mass on the kind of intersection of these two groups, and you can get that kind of behavior. So you can kind of like combine concepts. As long as the different models have learned different things, by ensembling them this way, you can kind of like combine them in interesting ways. Another example,
What's the difference between product and mixture? So if you use mixture, then these would look different.
So the difference is, if you think about it, like the product, well, as long as one of them basically assigns 0 probability, then the whole product evaluates to 0. And so the ensemble model, the product of experts, will also assign 0 probability. If you think about a mixture, even if one of them assigns 0 probability, as long as the others think this thing is likely, that thing will still have some probability. And so it behaves more like an OR, in the sense that as long as it's a soft OR, because it's yeah, exactly. It's kind of like an average. Yeah.
How do we sample from this product of experts? How do we not, how do we ignore the Z part?
Yeah, how do we sample? Yeah, that will come up. There are ways to do it, it's just expensive. So it's not impossible. It's just like in an autoregressive model, it's very fast. In an energy-based model, you're gonna have to put more compute, basically at inference time, when you want to generate a sample. That's kind of like the price you pay.
Yeah, how is the product of experts related to the energy-based model, like formalism?
Yeah, so you can see that if you have individual probability density functions or probability mass functions, if you multiply them together, you get another function which is non-negative, but is not necessarily normalized. So to normalize it, you have to divide by this partition function, and from that perspective, it's an energy-based model. And so you can think of the energy of the product of experts as being the sum of the log likelihoods of each individual model. Because you can write p theta 1 as exp log p theta 1, and the other one as exp log p theta 2, and then it's kind of like the exp of the sum of the logs. The problem is that the sum of the log likelihoods, it's an energy, and it's not guaranteed to be normalized by design. And so you have to then renormalize everything with this global kind of partition function. Cool. Another example is the RBM, the restricted Boltzmann machine. This is actually an energy-based model with latent variables. And this one is a discrete probabilistic model where both the visible variables, let's say, are binary, and the latent variables are also binary. So you have n binary variables x and m latent variables z. Both of them, all the variables here are going to be binary. And for example, the x could represent pixel values, and the z is, as usual, kind of like latent features. And the joint distribution between z and x is an energy-based model, and it's a pretty simple energy-based model in the sense that there is the usual normalization constant, there is the usual exponential, And then the energy is just like a quadratic form, where you get the energy by, you have a W matrix, you have a vector of biases, basically B, and another vector of biases C, and you map the values that the X variables have and the Z variables have to a scalar by just taking this kind of expression, which is just like a bunch of linear terms in the X's, a bunch of linear terms in the Z's, and then there is this cross product between the Xi's and the Zj's, which are weighted by those weighting terms, this weight matrix W. And it's restricted, it's called a restricted Boltzmann machine because basically in this expression, there is no kind of connection between the visible units or the hidden units. And so basically there is no xi, xj kind of term in here. There are interactions between the x variables and the z variables, but not between the x variables or between the z variables by themselves. Not super important, but the key thing is that this is actually one of the very first, it's kind of like important for historical reasons, it's one of the first deep generative models that actually kind of worked. They were able to train these models on image data by kind of stacking multiple RBMs. So an RBM is basically a joint distribution between visible and hidden. And then if you stack a bunch of them, so you have visibles at the bottom, and then you have one RBM here, and then you build an RBM between the hidden units of the first RBM and some other hidden units of the second RBM, and so forth. You get a deep Boltzmann machine. And kind of like the idea is that, okay, you have the pixels at the bottom, and then you have a hierarchy of more and more abstract features at the top. And it's actually pretty interesting that in the very early days of deep learning, people were not able to train deep neural networks very well. Like even in the supervised learning setting, things didn't quite work. And the only way they were able to get good results was to actually pre-train the neural network as a generative model. So they would kind of choose an architecture, which is kind of like this deep Boltzmann machine architecture. They would train the model in an unsupervised way as an RBM. So just as an energy-based model, they would train the weights of these matrices through some technique that we'll talk about later in this lecture. And then they would use that as initialization for their supervised learning algorithms. And that was sort of like the first thing that made deep learning work. And it was the only thing that worked initially, and they figured out other ways of making things work. Yeah, it was actually quite important for getting people on board with the idea of training large neural networks. And here you can see some samples of these kind of models. Again, this is a long time ago, 2009, but people were able to generate some reasonably looking samples by training one of these deep Boltzmann machines. And so you can see that sort of like the fundamental issue here is the partition function, this normalization constant. And just by looking through an example in the RBM setting, we can see why indeed computing the volume is hard. If you think about even just a single layer RBM, where you have these X variables, these Z variables, you have this energy-based model. Computing the exponential of this energy function is super easy. There's just basically a bunch of dot products. But the normalization constant is very expensive. Right? The normalization constant is going to be a function of W, B, and C. So the theta, the parameters that you have in the model, which in this case are these biases, B and C, and this matrix W. But computing a normalization constant requires you to go through every possible configuration, every possible assignment to the X variable, every possible assignment to the Z variables, and sum up all these unnormalized probabilities. And the problem is that there is basically 2 to the n terms in this sum, 2 to the m terms in this sum. And so you can see that even for small values n and m, computing that normalization constant is super expensive.
Is it to approximate?
Approximately, yeah, that's what we're going to have to do, basically. It's just like it's a well-defined function. It's just that if you wanted to compute it it doesn't have a closed form. Unlike the Gaussian case, there's no closed form for this expression, and brute forcing takes exponential time. So we'll have to basically do some kind of approximation. And in particular, the fact that the partition function is so hard to evaluate means that likelihood-based training is going to be almost impossible, because just to evaluate the probability of a data point under the current choice of the parameters requires you to know the denominator in that expression. And that's not generally known, and you're not going to be able to compute it. And so that's sort of like the issue. Optimizing the unnormalized probability, which is just the exponential, is super easy. But you have to take into account, basically, during learning, you need to figure out if you were to change the parameters by a little bit, how does that affect the numerator, which is easy in this expression. But then you also have to account how does changing the parameters affect the total volume? How does that affect the probability that the model assigns to everything else, all the possible things that can happen? And that is tricky because we cannot even compute this quantity, so it's going to be hard to figure out how does that quantity change if we were to make a small change to any of the parameters. If I were to change, let's say, b by a little bit, I know how to evaluate how this expression changes by a little bit, but I don't know how to evaluate how this partition function changes by a little bit. And that's kind of like what makes learning so hard.
Could you expand on the slide before where you showed like the samples, the generated samples from the RBM?
Mm-hmm.
How I didn't understand like how they how were they able to generate that? So I mean, you put in the observed pixels, and then you know with the stacking you can like learn the latent variables.
Yeah.
But how do they generate then the?
So yeah. So how do they generate? How do they learn? We haven't talked about it. That's gonna come up next. How do we do learning, and how do you sample from the models? Yeah, the problem is that even learning is hard because it requires evaluating likelihoods, requires the partition function, which you don't have. Sampling, as we'll see, is also kind of hard, and but there are approximations that you can do, and that's basically what they did. And kind of like the intuition is that if you want to do maximum likelihood learning, you have an expression that looks like this that you want to maximize. So you have a training data point, and you want to evaluate its probability according to the model, and then you want to maximize this expression as a function of theta. And the probability of a data point, as usual, is kind of like the unnormalized probability divided by the partition function, the total probability assigned by the model or the total unnormalized probability assigned by the model to everything else. And so if you want to make that ratio as big as possible, you need to be able to do two things. You need to be able to increase the numerator and decrease the denominator, which kind of makes sense. The intuition is that you want to figure out how to change your parameters so that you increase the unnormalized probability of the training data, while at the same time you need to make sure that you're not increasing the probability of everything else by too much. So what really matters is the relative probability of the training point you care about with respect to all the other things that could happen, which is kind of like what you get in the denominator, which is looking at the total unnormalized probability of all the other things that could have happened. And so essentially when you train, what you need to do is you cannot just optimize the numerator, because if you just increase the numerator, kind of like you just increase the size of the slice of the pie that you assign to the particular data point, you might be increasing the size of the total pie by even more. And so the relative probability does not even go up. And so you kind of like need to be able to account for the effect that changes the parameters theta has not only on the training data, but also on all the other points that could have been sampled by the model. And so somehow you need to increase the probability, the normalized probability of the training point, while pushing down kind of like the probability of everything else. And so it's kind of like the intuition that you have here. If this is f theta and you have the correct answer and some wrong answers, it's not sufficient to just push up kind of like the normalized probability of the correct answer, because everything else might also go up. And so the relative probability doesn't actually go up. So you need to be able to push up the probability of the right answer while at the same time pushing down the probability of everything else, of basically the wrong answers. And that's basically the idea. Instead of evaluating the partition function exactly, we're going to use some kind of Monte Carlo estimate. And so instead of evaluating the actual total normalized probability of everything else, we're just going to sample a few other things, and we're going to try to compare the training point we care about to these other samples from the model, these other wrong answers, these other negative samples. We have a positive sample, which is what we like in the training set. There's going to be a bunch of negative samples that we're going to kind of sample, and we're going to try to contrast them. We're going to try to increase the probability of the positive one and decrease the probability of everything else. And that's basically the contrastive divergence algorithm that was used to train that RBM, the DBM that we had before. Essentially, what you do is you make this intuition concrete by a fairly simple algorithm, where what you do is you sample from the model. So you generate kind of like a negative example by sampling from the model, and then you take the gradient of the difference between the log f theta, basically, which is just the kind of like the energy of the model, or the negative energy, on the trainings, minus f theta evaluated on the negative one, which is exactly doing this thing of pushing up the correct answer while pushing down the wrong answer, where kind of like the wrong answer is what is defined as the sample from the model.
How do we know that the sample we get is wrong?
Yeah, so the sample is not necessarily wrong. It's just like something else that could have come from the model. And we're considering it, it's kind of like a representative sample of something else that could have happened if you were to sample from the model. So we want the probability of the true data point to go up as compared to some other typical kind of scenario that you could have sampled from your model. And that's actually principled, as we'll see. This actually gives you an unbiased estimate of the true gradient that you would like to optimize.
It's still possible that the sample you get is also something that's from the training set, but like the overall, the estimation, the expectation is
the expectation. Yeah. Was there a?
Yeah, I'm still not clear. Like, how do you sample from that model? Like,
Okay. We haven't talked about how to sample, but if you could somehow sample from the model, then what I claim is that this algorithm would give you the right answer, and kind of like this idea of making the training data more likely than a typical sample from the model actually is what you want. So to the extent that you can indeed generate these samples, which we don't know how to do yet, but if you can, then this gives you a way of training a model to make it better, to fit to some data set. Yeah.
So when you draw a sample, you don't do like, if sample not present in training data, you just draw the sample.
You just draw a sample, yeah, whether or not it's in the training set, yeah, it doesn't matter, yeah. And so why does this algorithm work? Well, if you think about it, what you want to do is, if you look at the log of this expression, which is just the log likelihood, you're going to get these two terms. You're going to get the f theta, which is just the neural network that you're using to parameterize your energy, and then you have this dependence on the partition function, the dependence that the partition function has on the parameters that you're optimizing with respect to. And what we want is the gradient of this quantity with respect to theta. And so just like before, we want to increase the f theta on the training set while decreasing kind of like the total amount of unnormalized probability mass that we get by changing theta by a little bit. And so really what we want is the gradient of this difference, which is just the difference of the gradients. And the gradient of the f theta is trivial to compute. That's just your neural network. We know how to optimize that quantity. We know how to adjust the parameters so that we push up the output of the neural network on the training data point that we have access to. What's more tricky is to figure out how does changing theta affect the total amount of unnormalized probability mass. And we know that the derivative of the log of z theta is just like the derivative of the argument of the log divided by z theta, just the derivative of the log kind of expression. And now we can replace z theta in the numerator there with the expression that we have. And because the gradient is linear, we can push the gradient inside this sum, and that's basically the same thing. We know that z theta is just the integral of the unnormalized probability, and then we can push the gradient inside, and we get this quantity here. And now we know how to compute that gradient using chain rule, and that evaluates to that. It's just the gradient of f theta again. This is something we know how to compute. And then it's kind of rescaled by this exponential and the partition function. And if we push the partition function inside, you'll recognize that this is just the probability assigned by the model to a possible data point x. And so the true gradient of the log likelihood, which is what we would like to optimize and do gradient ascent with respect to, is basically this difference, is basically the gradient of the energy evaluated at the data point minus the expected gradient with respect to the model distribution. Which kind of like makes sense. We need to figure out how does changing theta by a little bit affect the unnormalized probability that we assign to the true data point we care about. And then we also need to understand how changing theta affects the probability of everything else that could have happened. And we need to weight all the possible x's with the probability assigned by the model for the current choice of theta. And now you see why the contrastive divergence work. The contrastive divergence algorithm is just a Monte Carlo approximation of that expectation. So we approximate the expectation with respect to the model distribution with a single sample. And that's an unbiased estimator of the true gradient. And so the true gradient is basically this difference between the gradient evaluated at the true data point and the gradient evaluated at a typical sample, what you get by sampling from the model. And as long as this, you can follow this direction in your gradient ascent algorithm, you are making the relative probability of the data increase, basically, because kind of like the relative the data goes up more than the denominator, than how much the partition function grows, essentially. And that's kind of like the key idea behind the contrastive divergence algorithm. The main thing that we still remains to be seen is how do you get samples, right? We still don't know how to sample from these models. And the problem is that, well, we don't have a direct way of sampling like in an autoregressive model where we can just go through the variables one at a time and set them by sampling from the conditionals. And we cannot evaluate the probability of every data point because that requires knowing the partition function. But what we can do is we can compare two data points, or we can compare two possible samples, x and x prime. And the basic idea is that we can do some kind of like local search or local optimization where we can start with a sample that might not be good, just by randomly initializing x0 somehow. And then trying to locally perturb this sample to try to make it more likely, essentially, according to the model. And because we can do comparisons, checking whether the sample or its perturbation is more likely is going to be tractable. And so this is a particular type of algorithm called the Markov chain Monte Carlo method. It's actually pretty simple. What you do is, again, you initialize the procedure somehow, and then at every step, you propose basically some change to your sample. And it could be as simple as adding some noise to what you have right now. And then if what you get by perturbing your sample has higher probability than what you started from, which we can do, we can do this comparison because we don't need the partition function to compare the probability of x prime with what we have right now with xt. Then we update our sample to this new candidate x prime. And then what we need to do is we also need to add a little bit of noise to the process, where basically, if you think of this as an optimization problem, we're always taking uphill moves. So if the probability goes up, we always take that step. And but if x prime, this proposed transformed sample that we get by adding noise, actually has lower probability than what we started from, we occasionally take these downhill moves with probability proportional to this quantity. So basically proportional to how much worse this new sample we're proposing is compared to where we started from. And then you keep doing this. And it turns out that in theory, at least, if you repeat this procedure for a sufficiently large number of steps, you will eventually get a sample from the true distribution.
Why do you need to probabilistically accept the noise one instead of just ignoring it?
Yeah, great question. Why do we need to occasionally accept kind of like samples that are worse than what we started from? The reason is that we don't just want to do optimization. Like if you were to just do step one, then you would kind of like do some kind of a local search procedure where you would keep going around until you find a local optimum, then you would stop there. Which is not what we want, because we want a sample. So we want to somehow be able to explore the space more. And so we need to be able to accept downhill moves occasionally, and they are not too bad. And that basically allows the algorithm to kind of like explore the whole space of samples it could have generated, because maybe you're stuck in a local optimum that is not very good, and if you had moved much further away, there would have been regions with very high probability. And so you
discard it every time, you'll get the same sample.
Also, yeah.
So why do we just use the probability to go uphill as well? Why do we always go to the one with a higher?
Why we always go to the one with the higher likelihood? You could define other, this is not the only way of doing it. Like you could define other variants of this where you don't always accept uphill moves. There is a certain something called the Metropolis Hastings algorithm that you can use to kind of like define different variants of MCMC that would also work. This is kind of like the simplest version that is guaranteed to give samples, but yeah, there are other variants that you can use.
Aren't like the choice that you make in step 1 and 2 in that loop, in that condition, isn't that the same? Like in both cases, you take the x prime, right?
But in the second case, you only take it with some probability.
Okay.
So you always take an uphill. If your probability goes up, you always take that step. If it's a downhill move, then you take it with some probability. And if it's kind of like about the same, then you're likely to take it. If it's much worse, then this probability is going to be very small, and you're not going to take that kind of move. So that's the way you generate samples, and that's what you do in the contrastive divergence algorithm.